up with lesson 7.1 where I left off last class. So, example 3. And so lesson 0.71 is all about angles. Example 3, draw the given angle, 135 degrees. Whenever I draw an angle, I'm going to draw it in what's called standard form. So I'm going to start with that initial ray along the positive x-axis. Now 135 degrees is like 45 and 90. So right there would be 90. So I want 45 more. I'm eyeballing this, so don't take a projector to the screen. But that should be a roughly 135 degrees. Positive angles are created by rotating counterclockwise. Negative angles are created by rotating clockwise. You can see that in how I drew my 135 degrees. So here I have two angles, and I'm calling them alpha and beta. Those are two other Greek letters. We'll say this alpha is like 120 degrees. Again, I didn't measure it. Beta, I'm going to measure the other direction. See how that's going clockwise instead from that initial ray? That means that's going to be a negative 240 degrees. Alpha and beta are what are called coterminal angles because they have the same initial ray and the same terminal ray. Find three coterminal angles to 70 degrees. Well, here's that 70 degrees. I'm also going to have a negative 290 degrees. Okay, and that's just from 70 minus 360. Let me write that. Okay. I'm also going to have coterminal by rotating all the way around 360 and then another 70. So 70 plus 360, which is 30. Okay, so here's one. Here's another. So I can find another one by either rotating one full rotation negatively and then back to that negative 290, which would be negative 290 minus 360. Or I can do 430 plus 360. Both of those work. I'm going to go with that because of the addition. Okay. So radian measure of an angle is the ratio of the arc length to the radius. Okay. So this is my arc length, which is going to be my top. And my radius is down here, my denominator. So if I have here an arc length of 5 on the top and a radius of 5, my theta is going to be 5 over 5, which simplifies to 1 radian. Now you can write the label radian, but sometimes mathematicians just write 1. That's why it's really important to have degree, when it's a degree measurement, to have the degree symbol. Because if there's no symbol, it's implied that it's radians. Here we're going to have 8.2 over 4, which comes out as 2.05 radians. And again, you can write radians, or you can just write 2.05. I have seen some textbooks use like a fancy R, but it's not as common. So, 1 radian, and that's what we just talked about. 1 full rotation around a circle is 360 degrees. A half a rotation is 180 degrees. And a quarter rotation is 90 degrees. Let's look at that in radians. So here I have 1 radian where that radius is the same as that arc length. And then there's 2 radians and 3 radians. And see that little smidge left over? That's what makes it pi radians for half of a rotation. When you flip it over, 3, 2, 1, flip. That's why it's 2 pi. And here you can see the radius arc on that. So fancy. It'd be fancier if it showed the whole thing in the right order, but so one full rotation is 2 pi radians, half a rotation is pi radians, and a quarter rotation is going to be pi over 2. So these are all examples of quadrantal angles. I know, sounds very impressive. That's when the terminal side of an angle lies along either the x-axis or the y-axis, and they're always in degrees, multiples of 90. So here is going to be 0 because that's my initial right every single time. Here would be 90. Notice I'm rotating counterclockwise for that positive angle. 180 is going to be there. Oop, too far down, sorry. And 270 is down here. And when I want to do them in radians, I would have, and then actually, apologize, 360, because that's coterminal to 0 degrees. Here in radians, this is going to be 0 or it's going to be 2 pi, depending on if you haven't moved at all or if you've spun around the whole circle. This side will be pi. This side is half of pi. So basically, what I'm thinking about is this line is 0, 1/2, 1. This is going to be 3 pi, 2. And then that one's back to 2 pi. Okay. We good about my quadrantal angles? I hope so. I have no feedback. So. Conversion factors that we multiply between radians and degrees. So if I'm going from radians to degrees, I'm going to multiply by 180 degrees on the top over, look back to my chart, 180 degrees is the same as pi radians. I could do 360 and 2 pi, but that would just simplify by 2. So this is an easier way of doing that. And nobody wants fractions in their fractions. So this is, and I like to write radians so that when I'm doing my unit conversions, I can see that canceling happen. If I want to go from degrees to radians, I'm going to multiply by pi radians on the top and 180 degrees on the bottom. So let's do, from degrees to radians, let's do 135 degrees. So I'm going to multiply by pi radians on top. I'm going to have 180 degrees on the bottom. You can see my degrees canceling, top and bottom. And so I have 135 pi over 1. This is my radians. Again, you don't have to write radians. And I'm just going to do 135 over 180. I know you can't see it. And then I'm going to hit math and that first option that says frac. And that's going to simplify the fraction for me. So this is 3 pi over 4 radians. Convert the following radian measures to degrees. Let's do 2 pi over 3. So when I have 2 pi over 3, I'm going to multiply by 180 degrees over pi radians, because again, this was radians. And then I like to write radians so I can see them canceling, and it reminds me that I have it set up. My pi's are going to also cancel, and 2/3, oops, 2/3 of 180, that's really what I'm left with, 2/3 times 180. I can use my calculator, but it's 120 degrees. So some common radians, just a smidge, so I'll see the whole thing. So we already did our quadrantals. 2 pi, 2, and 2 pi. It might be a good idea to also do the degrees. I'm going to put the degrees in the answer. And if you have colored pencils or colored pens, you might want to do them in different colors. It's very snazzy. So directly in between 0 and 90, 45. Okay, and notice how that's half of 90? Well, half of a half is going to be a quarter. Okay. I also have here 30 degrees and 60 degrees. Well, that 30 degrees, that's a third of 90. 90 is a half, a third of a half, third of a half is 1/6. pi over 6. Now this one is doubling that. Doubling 1/6 would be 2/6, which simplifies to 1/3. Radians are just fractions. I think that's what trips people up the most about them, is actually that it's just fractions. Here I'm going to have 20, 135, 50. So then here in radians, I've got 1/6, 2/6, 3/6, 4/6. 4/6 is 2 over 3. 5/6, and then 6/6. Now, notice I skipped over the 35. That's because that's fourths. I've got 1/4, 1/2, 3/4, 4/4. Okay. And then 10. All right. So this will be 7 pi over 6. And then 8 pi over 6, which I can simplify 4 pi over 3. Actually, I gotta keep going. 9 pi over 3 over 6, which simplifies to 3/2. 10 pi over 6, which is 5 pi over 3. And then 11 pi over 6. Alternatively, I could take all of those degree measures and do all my conversions from them as well. I'm just showing you a shortcut. So 3 pi over 4, 4 pi over 4. This will be 5 pi over 4. 6 pi over 4, which simplifies to 3 pi over 2. And then 7 pi. I should put the degrees on these though. 300, 315. And those are some common radians. You can also have negative angles. So like 11 pi over 6 is coterminal to negative pi over 6 if I rotated this way instead. So, all right. Angular velocity. Angular velocity. And you could pause right now and do some of the practice problems in the homework. That's okay. I'm going to just go into the other part of this lesson. Okay, so I gave you some time if you want to pause. Angular and linear velocity. So give the degree measure and the radian measure of the angle formed by the hour hand and the minute hand at 2:30 p.m. Now this one's kind of a tricky question. So I'll give you a moment to draw the clock. And a reminder, at 2:30, the big hand is down, and the little hand is not pointing at the 2. I'm going to repeat that. The little hand is not pointing at the 2. The little hand is actually going to point in between the 2 and the 3 because it's halfway between them. So I've got 90 here. This is a little sliver of 15 degrees. So I have a total of 90 and 15, which is 105 degrees. Tricky, tricky, tricky. So angular velocity is the rate in which a gear is turning. It's measured in revolutions per minute or radians per minute. Sometimes you even see degrees per second. So, and solved with dimensional analysis. A gear revolves at 40 revolutions per minute. So 40 revolutions over minutes. Find the number of degrees per minute through which the gear turns. So I already have minutes. I need to convert from revolutions to degrees. Well, one revolution is 360 degrees. So I'll have 360 degrees on the top and one revolution on the bottom. And so that gives me degrees per minute. Find the number of radians per minute through which the gears turn. So again, I'm going to start with that same 40 revolutions per minute. And I'm going to do, instead of one revolution being 360 degrees. In radian measure, 1 revolution is 2 pi radians. I have 2 pi radians. Again, I still put radians. I don't need to, but I like it because it keeps me organized. And I'll have 80 pi radians per minute. A wheel is rotated at 50 revolutions per minute. Find the angular speed in radians per second. Take a moment, pause the video, and try this problem. Okay, did you try it? All right, so we're doing 50 revolutions per minute. Find the angular speed in radians per second. So my goal is to have radians on the top and seconds on the bottom. I'm going to do the seconds first. 1 minute is 60 seconds. And then 1 revolution is 2 pi radians. My revolutions cancel, my minutes cancel. And I'm left with 100 pi radians on the top because I'm multiplying 50 times 1 times 2 pi. And 1 times 60 times 1 over 6. 10 pi over 6 radians per second, which simplifies to 5 pi over 3 radians per second. You can use mathfrak as long as you do not type the pi in. So I would be typing in just 100 divided by 60 and then mathfrak. As soon as you put the pi in, it won't be able to mathfrak it. All right. Last problem. A wheel on a tire is rotating at 30 miles per hour. Now this is a tricky one because that is not an angular. Oops, sorry. That is not an angular speed. That's actually what's called a linear speed because it's how far I'm traveling. So notice it doesn't say revolutions, it's miles. The tire's wheels have a radius of 15 inches. Find the angular velocity in revolutions per minute. Okay, so I want to get back to revolutions. First thing I'm going to do is do my time. 1 hour is 60 minutes. It's going to get me to minutes. Okay, now the tire wheel having a radius of 15 inches, what I'm going to do is find the circumference. Circumference is 2 r. 2 pi times 15, which is 30 pi inches. That's telling me in 1 revolution, I'm going to travel 30 pi inches. Right now I have miles, so we have to get it to inches. So I'll be able to get to revolutions. So 1 mile is 5,280 feet. 5 tomato. No, you do not need to have that memorized. 1 foot is 12 inches. That one I do expect you to know. And then 1 revolution is going to be 30 pi inches. You can see my miles canceling, my feet canceling, my inches canceling, and you can also see my hours canceling. So on the top, I have 30 times 5280 times 12. And then on the bottom, I have 60 times 30 times pi. And this is revolutions per minute, sorry. So one thing, if I'm going to type this in my calculator for the next step, I'm just going to move it over so I can see what I'm doing. 1900800. So the most common mistake on this, procedurally, is right here. Notice that I put that entire denominator with the pi in parentheses. Because if I don't do that, what's going to happen is it'll divide by 1,800 and then multiply that result by pi. And so pi won't be in the denominator, it would be in the numerator. So 336.1. And that is revolutions per minute. And that concludes this lesson.